Hi guys, today we're going to be teaching you guys how to do a chi-squared problem.
What is chi-squared? Chi-squared is the analysis of chance on genetic variation. Basically, this is seeing how likely is it that an observed outcome is due to chance. It is used because genetic ratios are never exact. So to explain what that means, the example we use are marbles. If you have a bag of 500 marbles, 250 red and 250 blue, and you were to pull out 100 marbles at random, 60 of them may be blue and 40 of them may be red. This is different from the ratio, but that could be due to chance, and chi-squared will determine whether or not this was due to chance.
So for the formula, you need to know a few symbols. So right here, it looks like x squared is what chi-square is. This means the sum of, and then this is the value. The O stands for observed, and the E stands for expected. So the observed values would be like the 40 and the 60 marbles we saw in the previous example, and the E would be expected. So we'd expect there to be 50 blue marbles and 50 red marbles, but it's not always like that.
In order to teach you guys how to do chi-square, we have an example problem. Multiple couples living in a small village in the eastern Africa lowlands, all of whom are heterozygous for the HBS allele, have 500 children among them. Of these children, 139 are homozygous for HBA, 279 are heterozygous for HBS, and 82 suffer from sickle cell disease. Is this data statistically significant? Explained using a chi-square statistical analysis test.
So the first thing we're going to do is pick out all the important information because there's a lot of information that we really don't care about. So the parents both being heterozygous is essential to create your ratio. Then there being a total of 500 children is important. 139 that are homozygous, 279 that are heterozygous, and 82 that suffer from the disease. These are all important facts that we need to create our ratio and therefore fill our table.
So before we can start solving for chi-square, we have to be able to write a null hypothesis. The null hypothesis basically would say that any deviation from what is observed and what is expected is due to chance. So in this case, if a heterozygous male and a heterozygous female were to give birth to, how many was it, 100 offspring, then the ratio would be 1 to 2 to 1, and any deviation from this is solely due to chance.
So the first thing we're going to do is create a chi-squared chart. And this is basically just the equation we showed you guys before, but in a chart form. So we kind of spread it out and it's easier and it keeps it more organized. So we put all of our subdivisions of the different possibilities over here. And then all of our observed values, our expected values, our observed minus our expected values. And then we take this quantity and we square it and we divide it by the expected. And then once we get all of these values here, we're going to add all of these values together to get the chi-squared value. And then this is the number we're going to be working with, whatever chi-squared equals. So we inserted our information. Since the ratio is 1 to 2 to 1, our expected is going to be those 500 offspring kind of like subdivided into the 1 to 2 to 1 ratio. The observed is whatever number we got from the problem. And what we're going to do is we're going to subtract the expected from the observed. And then this is the number we get over here. And then we're going to multiply it by itself, which is squaring it. And then we divide it by the expected value, which is over here. And then that's what's going to give us all these numbers right here. And then once we add them together, we're going to get our chi-squared value, which is 19.72.
Alright, once you find the chi-squared, you're not finished with the problem. The next step is calculating the degrees of freedom. And to calculate the degrees of freedom, you basically take the number of possible genotypes and subtract it by 1. So since there was homozygous, dominant, heterozygous, and homozygous recessive, you have 3 options, and you would subtract that from 1 to get 2. So the degrees of freedom would be 2.
So after that, there's going to be a chart you guys get. And what we use is 0.05. So since the degrees of freedom is 2, we find 2 on this column and then 0.05 in this row. And when it meets up, it's 5.991, and that's our p-value. And that's important in deciphering whether or not we're going to reject or fail to reject our null hypothesis.
So once you get the p-value, you can now decide whether to reject or fail to reject your null hypothesis. If chi-squared is greater than the critical value, you reject the null hypothesis. If chi-squared is less than the critical value, you fail to reject the null hypothesis. In this case, chi-squared will equal 19.72 and the p-value was 5.991. So you would reject the null hypothesis.
So if you're still confused, here's another example. Let's say if there's 100 heterozygous males that mate with 100 homozygous recessive females. The observed value is 56 heterozygous and 44 homozygous recessive. Find chi-square. So if 100 heterozygous males and 100 homozygous recessive females had children, then the expected value ratio of their children would be a 1-to-1 homozygous recessive ratio, and any deviation is due to chance. And this is how we know it. We're going to use a monohybrid cross, and we're crossing the heterozygous male with the homozygous female, and we can see that the 4 offspring that they produce is 2 heterozygous and 2 homozygous recessive, and a 2-to-2 simplifies to a 1-to-1. So as we did before, we're going to use that same table, and we're going to fill in the values, and we're going to find chi-square. So our observed was 56 and 44, and we're going to expect it to be 50-50 because it's a 1-to-1 ratio, and there's 100 in total. And then once we subtract it, we get 6 and -6, and then we square it and divide it by the expected, and then that's how we're going to get 0.72 and 0.72. And we add those numbers, and chi-square equals 1.44. So for reject or fail to reject. Since there's only 2 options to pick from, our degrees of freedom is going to be 2 minus 1. And that equals 1 degree of freedom. So as before, we go on the chart and 1 degree of freedom, and we go to 0.05, and it's going to be 3.841. And that's your p-value. And since your p-value is greater than chi-square, because chi-square is only 1.44.
Now, when we say we fail to reject the null hypothesis, this basically means that we're not saying that the hypothesis is true. We're saying that it's wrong. It's wrong. It's not wrong, but it's not. We necessarily don't know if it's true yet because a hypothesis is not tested by chi-squared. So basically, it's leaving it to be an option that could be proven to be right.
Like, it can be affected by something outside, or it cannot be affected by something outside. Like, it doesn't only have to be due to chance.